addition of HX in alkenes involving rearrangement. Okay, let us consider a compound alkene 3-methyl-butane. When this is treated with HBr, according to Markovnikov rule, what happens? This electron is shifted to this carbon. H plus is attached to this carbon. As a result of this one, positive charge comes here. Okay, CH3, then CH, here it is CH3, here CH, single bond CH3. This carbon gets a positive charge. Br minus will be attached to this positively charged carbon. Then the expected product is nothing but CH3, CH, then CH3, then CH, CH3, Br on this carbon. This is the expected product. But this is not the actual product. What happens here? Listen here. As a result of this shifting, firstly, this carbocation is formed. There will be a rearrangement. For what purpose? For stable carbocation. Listen here, this carbocation is secondary. The carbon next to this positively charged carbon, that is this carbon, is a tertiary carbon. So when H minus is shifted to this carbon becomes positively charged carbon. What happens here? That I am writing here, H minus shift. Okay. So as a result of H minus shift, the carbocation is nothing but CH3C, single bond CH3. This carbon gets one more hydrogen, that is CH2. This is H minus is shifted to this carbon. This CH3 is already there. Listen here, the carbocation after rearrangement is nothing but a tertiary carbocation. Tertiary carbocation is more stable than secondary carbocation. Secondary carbocation is less stable as compared to tertiary carbocation. Okay, this is not a Markovnikov addition product. Now listen here, in final step, what happens? Negatively charged Br minus will be attached to this carbon. And the product is CH3, CH3, single bond CH2, single bond CH3, Br comes here. Okay. Consider this compound, that is 3,3-dimethyl-butane. As a result of Markovnikov addition, we are getting the carbocation like this. This carbocation is a secondary carbocation. Why? This carbon is directly attached to two other carbon atoms. As a result of shifting of one methyl group towards this carbon, that is CH3 minus, towards this carbon, what happens as a result of this shifting? CH3, single bond C, here one CH3, there is no change. Here CH, single bond CH3, this CH3 is shifted to this CH plus as CH3 minus. So CH3 minus and CH plus. What happens? Neutralization, and the CH3 group comes here. This carbon becomes positively charged. Okay. This carbocation is a tertiary carbocation which is more stable. What happens here? There is a shifting of CH3 group, that is known as methyl shift or CH3 minus shift. CH3 minus shift is the rearrangement takes place in this reaction. What happens as final step? Br minus, negatively charged Br minus will be attached to positively charged this carbon. As a result of this one, the product is CH3C, then CH3, CH, CH3, then here also CH3, here Br comes. This is the product. Okay. Now consider another question, that is one alkene, and what is the product of hydrobromination of this alkene? Br comes here. This is the expected product. This is the Markovnikov product also, but this is not the actual product. What happens? Here one hydrogen will be there. That H minus is shifted to this position. As a result of that one, the product will be like this. That is ethyl group is present here and Br comes here. This is the product. Okay. Now listen here, I am discussing mechanism also. That is in first step what happens. In first step what happens? Here it is, the plus charge comes here. This shifting H minus, H plus will be attached to this carbon. So this will be the carbocation. This is secondary carbocation, which is less stable than tertiary. So for that purpose what happens, this H plus, H minus will be shifted to this carbon. Okay. As a result of this one, the carbocation formed is nothing but this one. Okay. Br minus attached to tertiary carbocation. This is tertiary carbocation, which is more stable. Normally these rearrangement reactions will take place with a low rate. Why? The speed will be less because the time is taken for this rearrangement. Okay. Now another question, that is let us consider this compound, this alkene. When this alkene is treated with HBr, which will be the product? You can say very easily, the product is nothing but, listen here what happens as a result of rearrangement. Okay, normally what happens, Br is expected to come here because here CH2, here CH. So Br minus will be attached to this positively charged carbon or secondary carbocation. That is the Markovnikov product. But in this case, if this CH3 is shifted to this position, then this carbocation will be more stable because it is tertiary carbocation. Okay. So what happens? The final product will be methyl group is present here. This is the product. So what happens here? As a result of this first shifting, the carbocation formed is nothing but, listen here, this is the carbocation formed, first step. But this carbocation is a secondary carbocation. So what happens? CH3 minus shift, methyl shift takes place. That is, this methyl group is shifted to this carbon. The intermediate is nothing but a tertiary carbocation. Okay, Br minus is attached on this tertiary carbocation to form this product. Consider these two questions. These are not from hydrohalogenation but are from hydration. Okay, normal hydration in presence of dilute H2SO4. Then you can predict the answer. What is the answer for the first question? That is written here. We are expecting OH here, H here and OH here, but OH comes here because here the carbocation will be secondary, here the carbocation will be tertiary. So the product will be OH comes here and this one methyl group is shifted to this position. This is the answer. Okay. In this case what happens? If plus charge comes here, that will be secondary carbocation. If plus charge comes here, that will be tertiary carbocation. So the product will be on this carbon. Its OH will be attached on this carbon. Okay. Hydride is shifted to this carbon. There is no need of showing hydrogen here because hydrogen is hidden on this carbon. So this is the product in this case. Now stereochemical aspects of electrophilic addition reaction. Okay, before discussing the importance of stereochemistry in electrophilic addition reaction, let us consider a simple example, that is this one. Here one CH3 group, then here one double bond. Okay. What is the addition product of this one with the HBr? So firstly, we have to consider two types of carbocation formed from this one. That is by shifting towards this position and by shifting towards this position. So first carbocation is nothing but this will be the one carbocation plus this will be the other carbocation. That is positive charge will come here. This will be the other carbocation. Okay, which is the most stable one? In this carbocation there is no resonance. Next we have to search for hyperconjugation. This is alpha hydrogen. This is also alpha hydrogen. So here alpha hydrogen is equal to 4 in this case. Okay. Here 2 hydrogen atoms, here 2 hydrogen atoms. In this case, this is alpha hydrogen, this is alpha hydrogen. Here also alpha hydrogen is equal to 4. So hyperconjugation is not applicable in this case. Then we have to consider inductive effect. CH3 group is plus I group. Okay, being plus I group, CH3 pushes the electron like this. So as a result of the pushing comes here. You know that stability of carbocation increases due to the decrease in positive charge on carbon. Okay, out of these two carbocations, on which carbon positive charge will be less? On this carbon or this carbon? Definitely this carbon. Why? Here the inductive effect is more than this carbocation. Here the positively charged carbon is far away from this CH3 group. Here the positively charged carbon is somewhat near to this CH3 group as compared to this one. Okay. So as distance increases, inductive effect decreases because I effect, inductive effect is distance dependent. Distance dependent effect. Distance dependent effect. That is, distance increases, inductive effect decreases. Are you okay? So this will be the major product. That means this is a more stable carbocation. The product is, this one is the product. Now you may have a doubt, if this carbocation is formed, then as a result of hydride shift from this carbon to this carbon, then we will get a carbocation which is more stable than this one. We are expecting like that. Listen here. Now what happens? Here positively charged carbon is very near to CH3 group. So here positive charge will be very less. So why this is not formed? As a result of rearrangement for the formation of more stable carbocation. But here we have to think that, listen here, we have to consider resonance first. There is no resonance. Next we have to consider hyperconjugation. We are considering hyperconjugation in this structure. Alpha hydrogen is equal to 4. But in this structure, this is alpha hydrogen, this is alpha hydrogen. So alpha hydrogen is equal to here 2 and here 1, 3. So this contain more number of alpha hydrogen. So hyperconjugation is more in this case. If hyperconjugation is there, we should not consider inductive effect, because resonance is more important than hyperconjugation, which is more important than inductive effect. Okay, here inductive effect is maximum, here inductive effect is minimum, but here hyperconjugation is maximum, here hyperconjugation is minimum. So we have to consider hyperconjugation. So this is the more stable carbocation. So there will never be no H minus shift there will never be hydride shift. Okay, but here there is nothing regarding stereochemistry. Next, we have to check the importance of stereochemistry in this type of reaction. Okay, instead of this one, if we are given like this is wedge and dash formula. If the formula is given as wedge and dash formula or three-dimensional formula, then we have to check whether there is stereochemical importance or not. Okay, there are two types of product can be formed as a result of the reaction. That is, listen here, first one is Br, that will be going away from the plane of this hexagonal ring. This is coming out from the plane of this hexagonal ring. The second expected product is, listen, we are discussed, that means Br will come only this position, but if you are discussing three-dimensional formula, then two types of product can be formed. First one is this product and second one is this product. Here CS3 and Br on same side, here CS3 and Br on opposite side, and also these are not the mirror images. Okay, these are stereoisomers, that is, there is difference in three-dimensional arrangement of these two structures. The stereoisomers which are not mirror images of each other, not mirror images, but stereoisomers. Stereoisomers. What are those? They are known as diastereomers. Diastereomers. Okay. So the products of hydrobromination of this alkene are diastereomers. You got it? Let us consider this compound, that is CD3 C double bond CH2 PH. Okay, one Br is also attached here. After breaking this double bond, the fourth different group comes here, that is Br. Then definitely this carbon will be a chiral carbon. Okay, so after the addition, there is the possibility of the formation of a chiral compound. That is the importance of stereochemistry in this reaction. Okay, so what is the product of hydrobromination of this compound? So firstly, what happens, we have to discuss the mechanism. This is the carbocation formed from this one. Okay, H plus is attached to this carbon which carrying maximum number of hydrogen atom. The geometry of carbocation is triangular planar. So by discussing the stereochemical importance of this reaction, there are two types of addition takes place. Listen here, very important. Br minus can come through this way and Br minus can come through this way. Okay, that is there will be the formation of two different types of stereoisomers. That is, listen here, if you are giving the Fischer projection formulae, here CD3, here PH, here CD3, here PH, then what happens? In first case, if Br comes through this side, then Br comes here and CS3 comes here. In this case, CS3 comes here and Br comes here. Look at these two. What is the relation between these two? These two are mirror images of each other. Are you okay? CD3, CD3, CS3, CS3, PH, PH, Br, Br. Two isomers, optical isomers, two stereoisomers or optical isomers, which are mirror images of each other. They are known as enantiomers. Enantiomers. Okay, we are using Fischer projection formula here because this is only just for information. So you should understand this one. That is, Br minus can approach C plus This carbon is a chiral carbon, this carbon is a chiral carbon, so they are optically active also. Okay.